For years, scientists have watched Betelgeuse with a mixture of fascination and unease. A red supergiant so massive, so unstable, that it seems to exist on the edge of catastrophe, like a giant ember slowly collapsing under its own weight. Every flicker, every dimming event, every irregular pulse has been recorded and studied. But nothing truly prepared anyone for what the James Webb Space Telescope has now revealed. Because this time, it wasn't just images. It was a transformation of data into something far more unsettling. A pattern hidden inside the dying light of a star. And when that data was processed using advanced quantum AI systems, something extraordinary happened. The machine began to see structure where humans saw chaos. Not noise. Not randomness. But sequence. A possible blueprint of stellar death itself. Betelgeuse has always been a star in transition. Massive, unstable, and nearing the end of its life cycle, it behaves less like a steady furnace and more like a collapsing storm. For decades, astronomers suspected that its core was entering the final stages of fusion, where internal pressure begins to fail against gravity's relentless pull. But those were models, predictions built on indirect evidence. James Webb changed that. For the first time, scientists were able to observe Betelgeuse in unprecedented resolution, not just in visible light, but across infrared wavelengths that penetrate deep into its chaotic outer layers. What they saw was not a calm progression toward collapse, but something far more violent. Enormous convective cells boiling across the surface. Plumes of plasma erupting outward like volcanic storms. Shockwaves rippling through layers of gas that should have been stable. And beneath it all, a rhythmic instability, as if the star itself was struggling to maintain coherence. At first, this was just astrophysics. Fascinating, but expected. Then the deeper analysis began. Behind every image captured by Webb lies an ocean of raw data. Photon counts, spectral shifts, energy distributions, timing variations. Normally, these datasets are interpreted through classical models, statistical averaging, and simulation comparisons. But in this case, a quantum AI system was used to push beyond traditional limits. What it found changed the interpretation entirely. Because the AI didn't just analyze the data. It connected it. Across time. Across wavelengths. Across layers of the star itself. At first, the system flagged irregular correlations between surface eruptions and internal energy shifts. Then it identified repeating structures in what should have been chaotic emissions. Then came the breakthrough. The system recognized that these weren't isolated events at all. They were part of a sequence. A chain of physical processes unfolding in a specific order inside Betelgeuse. As if the star was not merely dying, but executing a structured collapse. One researcher described it as looking at shattered glass and suddenly realizing the cracks form a deliberate pattern. What was once random now appeared directional. What was once chaotic now appeared procedural. And that is when the interpretation became unsettling. Because if the AI was correct, then Betelgeuse is not simply exploding outward in uncontrolled violence. It is transitioning through distinct stages of internal failure, each one triggering the next. Core instability. Shockwave propagation. Envelope destabilization. Mass ejection events. Pre-supernova restructuring. It wasn't just observation anymore. It was a decoded timeline. Like reading the final pages of a book written in fire and gravity. But the most disturbing aspect wasn't the surface activity. It was what lay beneath it. The AI detected that the star's internal oscillations were not purely thermal or gravitational in nature. Some of the patterns resembled feedback loops, systems where output influences input, creating recursive behavior inside the star's structure. In simpler terms, Betelgeuse appeared to be responding to its own collapse. Not consciously, of course, but structurally. As if different layers of the star were reacting to each other in a cascading chain of instability. That is where interpretation shifts from observation into something deeper. Because quantum AI doesn't just look for patterns in space. It looks for patterns in relationships between patterns. And what it found suggested that Betelgeuse's final stage is not a single explosion waiting to happen, but a multi-phase process that unfolds like a collapsing architecture. Each layer failing in sequence. Each failure triggering the next. Until the entire star can no longer hold itself together. Then comes the most controversial implication. The chemical signatures. As Betelgeuse sheds mass, it releases elements forged deep inside its core: carbon, oxygen, neon, silicon, iron. But Webb's data revealed something more subtle. Variations in these elements that appear structured, almost ordered. And when the AI analyzed those distributions, it suggested something unexpected. That the star's internal layers are not mixing randomly. They are separating according to density gradients in a predictable progression. In other words, Betelgeuse may be revealing its internal structure as it dies. Like an autopsy performed by the universe itself. This is where the narrative becomes almost uncomfortable to follow. Because the star is no longer just an object of study. It feels like a system exposing its internal logic in real time. And then comes the shockwave data. One of the most critical findings in Webb's observations was the detection of large-scale shock fronts moving through Betelgeuse's outer layers. These are not simple eruptions. They are signs of internal pressure waves, likely originating from deep within the star's core. The AI linked these shock waves across multiple observations and found something striking. They appeared to propagate in a structured sequence, almost as if one internal event is triggering another in a predictable chain reaction. This is the point where astrophysics becomes something closer to forensic reconstruction. Not guessing what might happen, but reconstructing what is already happening. And the implications are enormous. Because if Betelgeuse's collapse is structured, then its supernova may also be structured in ways scientists have never fully modeled. Not a single explosion, but a staged release of energy. A cascading failure of stellar equilibrium. And possibly, the formation of its remnant object, neutron star or black hole, may depend on asymmetries already visible in the data. Then comes the quietest but most unsettling idea of all. The AI didn't just identify patterns in Betelgeuse. It identified relationships between observation and structure. Meaning that what we are seeing is not just a dying star. It may be a readable process. A sequence that can be decoded in real time. Like watching the universe write instructions in light and plasma. And slowly, carefully, allowing us to read them. That is why this moment feels different. Because for the first time, telescopes are not just capturing images of a star. And AI is not just classifying data. Together, they are revealing something closer to translation. Turning cosmic violence into something structured enough to understand. Something almost narrative in form. But the final question remains unanswered. If Betelgeuse is revealing the structure of its own death in observable patterns, then what else in the universe is doing the same? How many other stars are already in this state of hidden readability? And how long before we realize that what we call chaos in the cosmos is actually information we haven't learned to decode yet? Betelgeuse is still out there, still burning, still collapsing slowly across cosmic time. But now it feels different. Less like a distant object. And more like a message unfolding in real time. A giant star not just dying, but telling us how it dies. And the most unsettling thought of all is this. We may have just learned how to listen.